So the pigment is between the spheres of silica. And that's why we see this perfect rendition of a stick. This is black opal. Sure enough, all of it, the whole thing, is black opal, cleverly disguised as a stick. But all it is the pigment that's left over. Okay, so this opal formed under it's a chemical reaction. It happens every time. It's not magic. It's not some guy in the sky making it. It's a chemical reaction. Happens every time those things come together in the right proportions. It can't help it. It always does it. And that's what science is all about. Huh? So the opal formed and got hard, and in some subsequent geological activity, it cracked again. And those cracks filled in with kaolinite clay. And so this was a going opal, a real opal, the stone you see here, and it cracked in 3 places. Boom, boom, boom. And some other places. I mean, there's some places around you can see. Well, I don't know. That's probably the wood part. It's rotten wood now, so there's gaps in the wood and little holes in it and stuff. So it's not always pristine looking, right? It looks like rotten wood. But these cracks filled in with kaolinite clay. And they re-opalized. And they were clever enough to match the opal that's in the stick already. Probably because the kaolinite clay is all the same size. That's what makes really bright opal really bright, because the spheres of silica are all homogeneous in size. They have to be half the size of the wavelength of visible light in order for Bragg diffraction to create these rainbows that you see. The colors aren't inside the stone. There's nothing red or green or blue inside that stone. It's just light breaking in the structure of the stone. The little spheres of silica are arranged in a very orderly fashion. And they do that automatically, all by themselves, because that's what spheres do when they're all one size. They fit together just like that. It's called face-centered hexagonal. So there's 6 spheres around each sphere in a plane, or 36 spheres in a 3-dimensional unit. And that orderliness also includes the spaces between the spheres. So if you put stuff in the spaces between the spheres, see what happens? Well, that pigment there is stuff between the spheres, and you don't get any play of color. So if you tried to dye some opal black, right, guess what would happen? Oh, shitsky, huh? So anyway, there it is, folks. It's precious opal, black precious opal, the finest black precious opal in the world because of all that iron sulfide in the environment. That's what makes black opal black. And it's the finest black opal in the world. Peace. Oh, haha. Speaking of between the spheres, this is treated opal. I treated it with more hydrogen peroxide and sulfuric acid. The stuff is called piranha solution, right? And we use it to clean organic material off metals, basically. But it also makes precious opal. Nobody knew that till Len Cram came along. He told Paul Downing about it. He wrote an article, and I read it and figured it out. And this sat in that piranha solution, brand new, clean piranha solution, kind of sideways. So the line that you see there is the line of the acid. And it removed the sulfides from between the spheres because the clay that was left over that didn't opalized when I put it in the piranha solution. It made the play of color change in this opal. And it removed all that stuff from between the spheres. How about that, huh? Isn't that cool? So that's what happens when you treat opal. It doesn't get better, man. It does not get better. You cannot make better opal by treating it. You can't. It is not science. It is a lie.